Hello, science fans! Today let's talk about a truly amazing material, titanium. Imagine a metal that is as strong as steel but weighs about half as much. That's titanium for you. It's a shiny, silvery gray element that has some seriously cool superpowers. One of its best tricks is that it doesn't rust or corrode easily, which means it can stand up to salt water and harsh chemicals without breaking a sweat. This unique combination of being strong, lightweight, and tough against corrosion makes it incredibly valuable for some of the most important jobs in the world. Because of these fantastic properties, you can find titanium everywhere, doing some very impressive things. In the aerospace industry, it's a star player. Engineers use it to build parts for airplanes and spacecraft that need to be both incredibly strong and as light as possible to fly efficiently. Doctors and surgeons also rely on it for medical implants like artificial hips and dental fixtures. Since our bodies don't reject it and it's so durable, it can stay inside a person for a lifetime. It's also used in high-performance sports equipment like bicycle frames and golf clubs to give athletes an edge. Now you might be wondering, if titanium is so great, where does it come from? It's actually the 9th most abundant element in the Earth's crust, so there's a lot of it around. However, you won't just find a big, shiny chunk of pure titanium lying on the ground. It's a very social element, which means it loves to bond with other elements, especially oxygen. This means it's always found locked away inside different minerals. The two most important minerals that carry titanium are called ilmenite and rutile. These look like dark, sandy, or rocky materials. To get these titanium-rich minerals, we have to go mining. The biggest sources of these minerals are found in places like Australia, South Africa, and Canada. Miners use large machines to dig up the ore from open-pit mines, which are like giant bowls carved into the earth. Once the ore is extracted, it's crushed into smaller pieces and washed carefully. This process helps to separate the heavier, valuable ilmenite and rutile from all the other rock and sand. After this step, the concentrated minerals are finally ready for the next stage of their incredible journey: becoming pure metal. Once we have our concentrated titanium minerals, the real science magic begins. The biggest challenge is getting the titanium to let go of the oxygen it's so tightly bonded to. For many years, this was a very difficult problem to solve, which is why titanium was so rare. Then in the 1940s, a brilliant scientist named William J. Kroll invented a method that we still use today. It's called the Kroll Process, and it's a multi-step recipe for turning ore into pure titanium. It's a tough, energy-hungry process, but it gets the job done and unlocks the metal's amazing potential. The first major step in the Kroll process is called chlorination. Think of it like a chemical swap. We take the titanium ore, which is titanium dioxide, and mix it with a carbon source, like coke, that's baked coal, and hot chlorine gas. This mixture is heated up in a massive reactor to about 1,000 degrees Celsius. At this extreme temperature, the chlorine kicks the oxygen out of the way and bonds with the titanium instead. This reaction creates a liquid called titanium tetrachloride. All the other unwanted stuff, like iron, is left behind as a solid, making this a great first cleaning step. Next, the liquid titanium tetrachloride needs to be purified even more. This is done through a process called distillation. It works just like distilling water. You heat the liquid until it turns into a gas, leaving any heavier impurities behind. The titanium tetrachloride gas is then collected and cooled back down into a super pure liquid. This step is extremely important because even tiny amounts of impurities can make the final titanium metal weak or brittle. We need it to be as clean as possible to get that legendary strength we're looking for. It's a bit like filtering coffee to make sure you only get the good stuff. The final step is the most dramatic one: reduction. Here, we take the purified liquid titanium tetrachloride and place it into a sealed reactor with molten magnesium metal. The reactor is heated again, and all the air is removed to create a vacuum. In this intense environment, the magnesium proves to be even more attractive to the chlorine than the titanium is. The magnesium atoms pull the chlorine atoms away, leaving the titanium all by itself for the first time. What's left behind isn't a shiny ingot, but a porous gray material called titanium sponge. It looks a bit like a sea sponge, and it's finally pure titanium metal. That titanium sponge we just made is pure, but it's not very useful in its spongy form. You can't build an airplane wing out of a brittle, porous block. So the next step is to transform it into a solid, usable metal. This is done by melting it. The sponge is pressed into compact blocks and placed inside a special furnace. Because titanium reacts so easily with air when it's hot, This has to be done in a vacuum. A common method is called vacuum arc remelting, where a powerful electric arc, like a controlled lightning bolt, melts the sponge into a pool of liquid titanium. While the titanium is being melted, it's a perfect time to make it even stronger by creating an alloy. An alloy is a mixture of metals. Pure titanium is great, but mixing it with small amounts of other elements can enhance its properties, kind of like adding spices to a recipe to make it better. For example, the most common titanium alloy is made by adding a little bit of aluminum and vanadium. This famous alloy, known as Ti6Al4V, is incredibly popular in the aerospace industry because it's much stronger than pure titanium while still being just as lightweight and corrosion resistant. Once the melting is complete, whether it's pure titanium or a new alloy, the molten metal is poured into a mold to cool and solidify. This creates a large solid block of metal called an ingot. These ingots can be huge, weighing several tons. They are the basic building blocks from which nearly all titanium products are made. From this point, the solid titanium is ready to be shaped. The ingot is reheated until it glows bright orange, making it softer and easier to work with. Then, giant machines like presses and rollers go to work. Using immense force, these machines can forge, roll, and extrude the hot titanium into all sorts of useful shapes. Forging is like a blacksmith hammering metal, but on a massive scale to shape strong parts. Rolling squeezes the metal between huge rollers to create thin sheets or plates. Extruding pushes the metal through a shaped die to make long rods or tubes. Machining titanium into its final precise shape is very difficult because it's so hard. It requires special tools and techniques, but through this careful process we can create everything from a tiny medical screw to a massive structural beam for a supersonic jet. As amazing as titanium is, we have to consider its impact on our planet. The Kroll process, which is our main way of producing it, is a real energy hog. Heating those reactors to such high temperatures and running all the complex machinery uses a tremendous amount of electricity. This process also creates waste products like magnesium chloride that need to be managed carefully so they don't harm the environment. So, while the final product is clean and strong, the journey to get there leaves a significant environmental footprint that scientists and engineers are working hard to reduce. The good news is that titanium has some excellent green credentials that help balance the scales. One of its greatest strengths is its incredible durability and resistance to corrosion. A titanium part on an airplane or in a building can last for decades without needing to be replaced, which saves resources in the long run. Furthermore, titanium is highly recyclable. When a plane is retired or a medical implant is no longer needed, the titanium can be collected, melted down, and reused to make new products without any loss of quality. Recycling uses far less energy than making new titanium from ore. Looking toward the future, researchers are actively exploring new and better ways to produce this wonder metal. One of the most promising ideas is a method called the FFC Cambridge process. This technique uses electrolysis to extract titanium directly from titanium dioxide powder, which is a much simpler and potentially more energy-efficient path. It's like a scientific shortcut that could skip the complicated and energy-intensive Kroll process altogether. While this method is not yet widely used in industry, it represents an exciting possibility for making titanium production cleaner and more sustainable for future generations. In the end, titanium's journey is a story of incredible transformation. It starts as a common mineral hidden in the Earth's crust, and through a powerful and precise scientific process, becomes one of the most advanced materials known to humanity. Its unique combination of strength, lightweight, and resilience makes it essential for pushing the boundaries of technology, from exploring the skies to healing the human body. As we find greener ways to produce it, this superhero metal will undoubtedly continue to play a vital role in building a stronger, more efficient, and more innovative future for us all.